measurement and measurement in quantum mechanics. That is, so there are several topics. First one, we say that if we do the measurement like this operator affects on the state and change another state, so that is perturbs the states, right? That is not. And then we know these states, according to the postulate 3, just be one of the eigenstates of A, and the values be, and that is postulate 3. Okay, so that is first issue. Second one, since when we perturb the states and if we go to one of the eigenstates of A, then what is the probability to find one of the states, right? So that is a probability. That is this postulate 4. Okay, here, that is normalization. Please be careful. Do not miss this one because usually if this is not normalized, you have divided by this factor. That is, okay. Check your homework. Thank you. And so that is, yeah. And then since we know that the probability to get output with one of these, so we get this probability, then that means the output has a distribution, and we want to know which one are the most possible and which one is less possible. So we usually look this expectation value. That gives us the distribution of this outcome. Again, here, if not normalized, you have this denominator here. And we already discussed that is just an index of A eigenvalue. It depends, so now I'm going to just A. So this is eigenvalue of A. Okay, I'm going to, yeah, here, right? Eigenvalue of A, and P and this A, right? That is a product, it is a probability, and this one is this. So that's the way for the discrete basis. I think that is we discussed end of last class. And today we keep continue for the, we are going to discuss for continuous basis how to obtain the expectation of operator A. Then we are going to discuss the measurement of the question is this. That is, if we want to measure the variable A and then measure B, does it give the different result or same result if we measure first B and second A? So that is the question here. Number 5. This one, then we introduce complete set of commutating operator. And then number 5, we are going to discuss the ancillary principle. Just review this, right? This one we have right. So that is today we will go to here because those will be covered by the midterm exam. So I think today is important that discuss. If you have any questions, stop me and we can expand the details. Now here, let's come here. So continue. How to obtain this expectation value of continuous basis? So now, by definition, right? That is here again. Let's just do. We always use this unity operator, since that will help us. So now let's continue here. I'm going to insert the unity operator. Do the same thing as before, the discrete basis. But in the continuum, unity operator is integral, right? So that is two integrals. Suppose we have from minus to infinite dA is for this one. Let me do this. Okay, I think I can do this one. Keep here, right? Keep broad, and then the first one minus 2. Suppose this this value of eigenvalue of A is A here, and then we know that be A, right? That is the first I, and then I keep A at here. Second integral is from negative infinity to positive, and I want to distinguish, I'm sorry, to distinguish these two sides, so I'm going to use A prime, and here A prime, right? That is numerator, and denominator, let's keep here. So that is 2I in the continuous basis, right? To integrate the unity operator. Then you can see here, you will see this is A operator, this is eigenstate of A, so we give A prime, right? This is A prime. And okay, so that's enough. So now let's, I can put this inside. I think Carol also asked sometimes when we can put inside us, because this is integral, is numbers, right? Eigenvalue, so I can put here. So now, dA, and this is bra psi and cat A. Then here I have cat A. Now A apply this A prime give us eigenvalue of A. Oh, I have another integral. Actually, let me do these two integrals together. So dA prime, and then psi A, and then I have A prime, A, sorry. This is a cat and bra, A here, A prime, is this one, right? And then we have the last one, A prime, psi. Okay, now you can see here, this is eigenvalues I can take, and then you can see here, let me do again, dA prime, I take A prime here, and here, this one is eigenstates, inner product of eigenstate A and A prime, that's the second, right? So we will have delta A prime, and then this one is psi A prime psi. Therefore, that means only when A equal to A prime, then the integral is non-zero, otherwise 0. So these two integrals become 1, right? And finally, and A equal to A prime, so I'm going to A, dA, okay, dA here. And then here, this A equal to A prime, so that is now what is? So now you can see here, I'm going to rewrite again. So this is not from A. Now here, this part, you can remember, we introduce probability for continuous basis. That is probability density, right? So here, if you remember, that is P. And then you can see you compare with this correct basis. So they are similar sum of all the possible eigenvalue. This is the integral from negative to infinite to the positive infinite. They sum over all the n. This is eigenvalue, and then multiply the probability. So the probability integral to whole, right? So that's the expression of the probability for the continuous basis. Okay, so that depends which basis we deal with, then which formula you're going to use, right? And the basic idea, everything the same. So now let's do one example and see how can we apply this this idea and the definition for example, how to obtain this after the measurement, to obtain this possibility and expectation value, right? Example here. So suppose the initial states here, right? Initial states we are going to measure these states. Give us is y1 plus 2 over square root 19 plus again another, oh, this is square root 2 plus okay. So that is not the eigenstates of operator which we are going to, so first let me give you what is here. It is eigenstates or vectors of operator Hamiltonian. And okay, so what that means, I mean, if I use EY, and let me use N, since I always use N. Right, that is means. Okay, and also the, so that is, this is so normal already. Orthogonal and normalized. Okay. So the it gave us here. It says so here En is equal to N epsilon. That is a epsilon is a constant that gives us a lot of energies. N how many? 1, 2, 3, 4, 5. Totally we have 5. And this form the complete, let's say just complete basis side. So complete, we know complete is sum of all together is equal to unity, right? And this orthogonal, it means it's, if not the same, they will equal to 0 if the same states in the product is equal to 1. Okay, now that is give us the information. Now ask us first, if we want to measure, right? So now we are going to measure the energy. That means Hamiltonian applied states, right? Like this, positively 3. So that gives us, we will go to one of the eigenstates of Hamiltonian, right? According to the positive 3. So question asks, which En we can get, and then what is the probability to get. The first question is, if we want to measure this system with these states, and we want to measure what? We want to measure energy. So what kind of output or outcome the energy will give, which and then corresponds to that by what is probability. So that is this one, right? And D, what is expectation value? That means the distribution of this outcome. So that is here, right? So we're going to go 1, 2, 3. Now, what basis is a discrete basis, right? So we are going to use this formula here, right? Okay, so now let's first A. Okay, first A. Okay, here, since we know this is not eigenstates of Hamiltonian, so what happened is when the Hamiltonian measure these states, it will give the possible states among these 5 eigenstates. So we're going to see is use this one, right? P and En is here, right? That is formula. That is, let's see for giving En how much the probability is. And the En here very easily, right? So you can N equal to 1, 2, 3, 5. So you have the eigenvalues. So now, here, since each probability has this denominator, you can do the denominator first, or see this inner product, right? Inner product, because, so now let's look at this one. That is, you will do the homework, so I will not do the details very easily. So you know this inner product is this product, and only since they are orthogonal, right? Only this same, they have a non-zero number. So first one is 1 over 19, right, square, right? Plus 4 over 19, second, plus 2 over 19, number 3, and number 4, 3 over 19, number 5 is 5 over 19, right? And totally, how many we have? 5, 10, 15, right? So that is not normalized. This is not equal to 1. That means when we do the probability, we have to include this term. Otherwise, your probability is not. So now, let's look. Okay. So now we are going to I think I want to make it safer quickly. So now it is equal to 1 to 5 Cn, right? Linear combination of this extent or superposition of these states in terms of these eigenstates of Hamiltonian, right? So here Cn is this coefficient here. I use this. So I'm going to give a general, and then you just substitute n equal to 1 to 2 to 3. So here Pn, En is equal to here, right? Let me write down here again. I think I need to use different. So now I'm going to use n prime since we have a summation n prime. That n prime. Do you agree? I use it because it's summation for all, so I have distinctly particular states, right? So you will see here summation n prime from 1 to 5, Cn prime, and then right? Then you can see here, this is orthogonal, so that means if I write down again n prime, Cn prime delta n prime square. So what means only when equal to n prime, right? Sum of all the n and O, so that is a Cn square. Not clear? Now what you need to just substitute the substitute the Cn square since you already got this inner product here, right? So for example, now let's consider n equal to 1, so P1 correspond to E1 is C1 square over C1 is this 1 over square root of 19, and C1 square is 1 over 19, and this is 15 over 19, right? So that is immediately got this. Right? This is this one, right? Here. So the remaining part I will not do, you just do the same thing. Okay. Now I'm going to do this topic, and then I'm going to discuss this. Now, this is for the expectation value, whatever this continuous spectrum or discontinuous spectrum or basis, you just depend on which basis you are going to use which formula. Now we want to discuss an important or very interesting topic. Is now so now we ask we are going to go to here. So why we are interested in this one? So now the question. The question is, okay, can we measure the two observables A and B simultaneously? or what's the condition, right? You can measure A, we know that how to do that. If this state is not any state of A, the probability to follow this. If the just one of eigenstates, so that definitely have a probability 1, the other is 0, right? So now the question, okay, after I measure A, now I'm going to measure B. What happened? Or I first measure A and then measure B. Are they the same result? Okay, so that is question. And the observables A and the B be measured simultaneously. Or, so the question, or we can say, if we measure, okay, A first, and B second, okay, on the same state, on the state, on this, okay. If right, so it does. The outcome, okay, different from that if we measure B first and A second. That means depend on order or not. So we measure the two, we want to see these states. For example, one is energy, another is momentum. So if we want to measure energy first and then measure momentum, they be the same. Yeah, question? Okay. In these states, is depend on measure the momentum first and measure the energy second. If not, that means we have to be careful, right? If yes, what condition? Yes. So that is the question here. Okay. Now the answer. The answer is we are going to according to what or basis on this postulate 3, right? Postulate 3. We know when the operator applied, when we do the measurement, what happened? It perturbs, right? Perturbs the states significantly in quantum mechanics. So that means that is the first thing we need to know this. Therefore, in general, we will measure this, we will perturb this to some other states. Then you do the second measurement for B, that go to this state, not this state, right? And then if you use B to measure this one, it will perturb another state, which is not this state, it's a double prime, right? So that is really not safe. So that is because this, right? So the result or the outcome, because of this, right? Outcome, the result of measure, we are going to measure in A and B will depend on the order of measurement. Or measurement, right? That is the answer. Now the key is how to know how it depends, why it depends. So now let's discuss examples, or we are going to examine what happens, right? So now we're going to examine. Okay. Examine. Okay. Let's look at the outcome of the two measurements. See, we use different order. Then let's see what is the outcome. Are they same or not? Why they are not same? Or why they same? Okay, so the two measurement. One is measure A first and B second. And second one is measure B first and A second. So let's see what happens. Okay, before we do that, let's first assume A, this is eigenvalue of A, phi A n. That gives us A n phi A n. So just assume, because it's eigenstate, usually we say that it is orthonormal. Okay. Second, B, if assume that psi Bm is its eigenvalues, eigenvectors, give the eigenvalue Bm. Then here we have also normal. Okay. This is a condition, right? This is known since we are looking for, and of course we all discuss this Hermitian, right? When they say measurement, all the Hermitian, since we discussed in quantum mechanics, postulate 2, all the observable has a corresponding operator with Hermitian. So this implies, okay, I will not. So you know this all real. Okay, those are followed. Now with this, so we are going to see. Let's look first. Okay, now first to make things simple, so it does not mean it will give a similar result, but so let's just initially assuming the initial state is just one of the eigenstates of operator A. Let this be a linear combination for any, right? But that is the previous example. But here we want to save time and we make it simple, so I just assume that is this. Okay, and also makes it simple, assume it's already normalized, since we know this eigenstates of operator A, and it's been normalized, right? Also normal. Okay, then let's consider first. Okay, first is, okay, first, let's see, measure A first and B second. Let's consider the first one. What will happen, right? So if this, then that first, A first, right? Oh, okay. If I write down clearly, so you may say why you need to go. So now A measure its states. And this state is nothing but the eigenstates of A. One of the eigenstates of A. Then according to the postulate 3, that will give us AN. Right? And this is what, this is the new states. But this new state is nothing but, it doesn't change. Since according to the postulate, if this is the eigenstate of operator A, when we measure it, will not change. It will not perturb. Only when this, if not eigenstate of operator A, it will perturb. Right? Okay. So now if this, then the probability, I'm going to use index n with AN, since it's only one AN value, right? Not any other values. That means outcome, if we measure these states with A, definitely the outcome is, the values be AN, and the states will not change. So the probability is equal to right? See here, is nothing but this phi AN, right? So here this 1 because the same state, and denominator also is already normalized. So the probability is 1. What does mean? There's no any other outcome. Only the outcome is that we definitely know this B given the value is AN, and state still keep the same state. That is the from the postulate, and we know that. So that is probability. Okay. Now, then consider the measure first, second. So now we are going to do B, right? Now we are going to do measure B. Now the B state is psi prime, right? Because when A measure this psi, we get a new, even though we know the state doesn't change, but we are going to use. I want to in general make this notation. Do not make mistakes. Then you know that it is nothing but it is the eigenstates of A, because prime is A. Okay. Now what happened? This state is not eigenstate of B. So the outcome should be among all the possibilities that among the eigenstates of B, right? And outcome the values be eigenvalue of B. So the outcome is among this, right? We do not know one of these and correspond to the one of the eigenvalue. Okay. Now, so the probability, now let's see, the probability to find this eigenvalue is Bm. How much? We need, by definition, it is the psi, right? So let me write down here. Project to this eigenvector of the B, psi prime. Here, the denominator also psi prime. Be careful. Since here it is a psi prime. If it is not the same, if it changes, so be careful here. The second one, so here, this one, we know psi prime is phi AN is normalized, so that is 1. Let me just rewrite here. Okay, how about this one? Okay, let me write down first, and then I'm going to extend. So I keep here. Be careful. This is eigenstates of A, but not eigenstate B. So this one, they are not orthonormal, right? So now next, because this one is already normalized, this is equal to 1, you know. The numerator is careful. Now, let's do this. Since psi prime, I'm going to extend this one in terms of linear combination of the eigenstates of B. Superposition principle, right? So I'm going to say CM B. This is the key. Do you understand? Any states can be expanded or expressed in terms of a linear combination of in the space. And the space now we select the space is formed by the eigenstates of the B. Any question here? Okay. Follow me, because homework, the midterm has this one. Something like this. Okay, if you have any question. All right, so now if this, let me substitute there, right? So now let me use this. So the probability of Pm, which is the eigenvalue of Bm, is psi m b. And now the psi an is summation, right? So now to distinguish, I'm going to use m prime, c m prime, b, psi m prime, b. Denominator already 1, so I just ignore that, right? This one is already 1, right? So I don't need red. And here, summation m prime, c m prime, b. Here, now you see this is the inner product of the eigenstate of operator B with different index. Here, that is. So summation for m prime only when m prime equal to n, then what is And how to determine this one? If you know the phi AN, you know how to determine, right? Any question after here?
I have a question.
Yes.
What is with the what's up with the with A and B like in the upper limit? I've not been able to figure out what that's meaning.
You mean why I do not make the upper limit?
No. I mean not the upper limit. Like you have psi m of B and then like psi n of A. I don't know what the A and B are marking here.
Okay.
I don't remember.
I use A as means this is correspond to the eigenvalue operator A. Sorry, it is index for operator A. So if I use A means this is eigenstates of operator A. If I use B, that is.
Okay.
Yeah, here B is eigenvector of operator B, just index.
Okay.
Okay, yeah. And the N and M is depend on different values. All right, so now good. So now that is measure for the find the probability or to if we obtain this eigenvalue of Bm. Now the question asks the total probability of finding what? Finding A equal to AN and B equal to BM. So what does mean? We are interested in, we do the measurement first A and second B. On this stage, we are going to see what is probability to get A just equal to AN value, one of the particular eigenvalue, and B is another the particular eigenvalue. So in that case, that means I'm going to say P to make index to distinguish the order which one is first, so I'm going to use, because A is first, right? So that's Pn, An, right? First. Okay, let me do this one. I use P, let's see the notation. Okay, just P, A, N, B, M. This index means the total probability for this continue two measurement. I gave us total probability is be equal to the first one is A, P, N, A, N, right? We need to measure the A is this one. And under this probability, we have another probability to measure BM, which is M, BM, right? That is total probability of measure these two values for these states. And how much it is? 1 multiplied Cm B squared. So that is a Cm B squared, right? Okay, so that is when we measure the first, consider the first one, measure A first and B second. Now we consider the second one to measure B first and A second. Let's see what happens. Okay, so do the same thing as for B first, right? B apply the states sign. Okay. That's B. B apply the states of one of the eigenstates of operator A, not B. Same thing like here, right? So then it will give us psi prime, which is equivalent to the among all these eigenstates of B. Right? We give this according to the postulate 4. Since this is not eigenstate of B, then what happens? The B, when we measure these states, it will perturb the states to one of the eigenstates of B. So that means the new states, psi prime in this case, is among them, then the probability to find the output of or outcome of this B value is Bm should be always keep in mind which one, which state. This one always the first before measurement. Right? After measurement, we want to know what is after. So when you do the probability here, this state is before measurement. Okay. Now, this before measurement is, okay, let me write down here. I think then you, so psi m b, because initial states is nothing but the eigenstates of operator A. So now, okay. Then come down to here. I already extend or express this eigenstates of operator A in terms of eigenstate of operator B with a linear combination. So it's a coefficient, right? So that is the denominator is 1 since normalized. The numerator here, again, if I write again, so now here, prime, C and prime, and then here, that and B, that and prime, B. And then we know this is orthogonal, so that n only when m equal to m prime, so that is C n. This is the probability to find this, measure the first B, and then get the probability. So that is not 1 since the states, initial state is not eigenstates of operator B. It is eigenstate of operator A. Okay, so that is the first. Now we go to the next. We are going to measure A, right? First B and second A. So A applied psi. After B measurement, the state change to a new state, right? And the new state, okay, let me first give us, it is one of the eigenstates of the B, right?
Shouldn't that be, those be phi right there?
This is a phi, this is a phi, this is psi. Which one? This is a phi. This is operator A's eigenstate. This eigenstate of operator B.
So if it's eigenstates of operator B, doesn't phi mean eigenstate and not psi? Or does it not matter?
This is the eigenstates of B, right?
Right, but I'm saying normally aren't don't we say that phi of something is the eigenstate, so, or is that not the right rule?
Okay, that's whether phi of psi is by definition. I initially gave the phi here.
Okay, I see.
Yeah, you just follow this. Because different person have different definition. We do not say that phi always eigenstate of psi. You just see, you have also in your, when you do the homework or your exam, you first give a definition here. Then I know what this means. Okay. So let me see here, the first one. Now I'll go to second. Okay. So now here, what is the prime? The prime be one of the eigenstates of B, right? So then I measure A. So now, since we are going to look at the same state here, so we are going to see this one is A. That means that after measurements, we go to one of the eigenstates of B. We are interested in B, the same Bm, since we are looking for this to outcome this eigenvalue the same, right? So we're looking at that eigenstates. Okay. So here, that will give us, according to possibility 3 and 4, that's be one of eigenstate of A, right? That is go to the side down. Then the probability to find AN is, by definition, I always use original definition, then we are going to substitute this into. So denominator is B, right? Initial states. And the numerator here is A, N, and then it's E. Now here we need to extend the eigenvector of operator B in terms of linear combination of eigenvector of operator A. since we are interested to project to A, right? Let's do this. Then we substitute. I think I can erase it. So I keep continuing here. That is A summation to distinguish n and n prime with n prime c n prime A sin n prime A square. And the denominator is 1, right? Because this is an eigenstate of P. So that is, I do not need right now. And you will see here n prime c n prime coefficient, and this one is, if you not use this orthonormal, and that gave us C N A. That make sense? Okay, now let's come to here. Again, we ask for total probability to find the eigenvalue, to find the observable A is AN, observable B is BM. When we do the A first, B second is this one. Now, how about this case? So again, the total probability of finding, we are interested in the same thing, of finding A equal to AN and B equal to BM. So that is, we are use index P. So this is A first and B second, right? But this be same, right? So now let me use BM first and A in second, because the number does not measure which one first, which one second. So this. So now let's see. First one, PMBM is this one. CM. Square, right? And then here, PNAN is this one. This is definitely not equal to, if we measure A first, A and B, right? So that means, yes, the measurement, it really depends on order. Let's be careful. And the reason is this measurement perturbs this, because it's according to the postulate A as 3, it will perturb these states.
I guess, okay, so
Yeah.
my only question about that so far, and maybe I'm getting ahead of myself, our initial question was, can we measure A and B simultaneously?
Yeah.
But we assume through our entire thing that we measure one and then the other, so not simultaneously.
Okay. Now the question, if simultaneous means if we measure A and B simultaneously, if the states still keep the same, or the outcome the same. If these two outcomes same, it doesn't matter which one is first, which one is second.
Right.
That means we can simultaneously measure these two values, get the same value, get this, give it a certain value, not uncertainty.
So if PBMAN equaled PANBM, we could say that it was simultaneous?
Yes, you can say that way. Yeah. Simultaneous means okay. Of course, you cannot measure simultaneously, right? Always 1, 2, right? I'm not sure you can design this machine or some of the device to measure this momentum and positions same time. But when we say simultaneous means this measurement will not affect or will not depend on order, which one first, which one second. That is this. Okay. Now, so now we have conclusion.
So you said you're not certain we can build a machine, which I buy that, but mathematically, we don't care about the limits of the machines. What, is it possible to mathematically take the two measurements simultaneously?
Mathematically, yes, that is we will discuss. If the mathematical simultaneity, that means it does not depend on which one we went first, which one second. You can consider this one as a one operator. If they are commute. So this is same thing. So you see that the C applied, it stays. Or if this is not same, so C prime applied stays. Is the result the same or not?
Mm-hmm.
Okay. All right, so now conclusion here. Oh. So in general, okay, in general we have already proved that this dependent order, right? That is we prove. And this one, what does mean? This means the commutator, right? So you can see with this two term is nothing but the commutator applied to the states. So because this one is not equal to 0, and what this means, they do not commute. Since states will not equal to 0. So we have this conclusion. If the measurement indeed depend on order of the measurement, then these two operator or the observable correspond to the operator, they do not commute each other. That means if the measurement depends on the order, then these two operators do not commute. Okay, I think we already have, so then A and the B do not commute. That is the first conclusion, okay. And then based on, that is maybe answer your question about simultaneous. Based on the Heisenberg uncertainty principle, we already discussed in chapter 2 and uncertainty principle. Okay. So the uncertainty of measurement variable A multiplied uncertainty of measure B if a simultaneous is equal to 0, right? So according to that, we always large or equal to the expectation value of the commutator. Remember this? So that means if this is, okay, if this is not equal to 0, then delta B is always larger 0. That is not simultaneous. And you cannot measure simultaneously. Always, when we say okay, now let me give this. Simultaneous means we can measure A and B and get exact value. If we have uncertainty, means it's not simultaneous. That makes sense to answer your question about simultaneous.
I think so the whole point of the idea of the term simultaneous here is saying that because A will force the state into a different eigenstate than is possible for B, you can't have both happen at the same time, because logically that would cause the state to go into two different states at the same time. It's not possible.
Yes. So you have uncertainty. That means you have a fluctuable. You cannot have the delta A equal to 0. And only things when this commute, right? So the commute, then we are going to discuss what is commute.
Does this imply that when operators do commute, they share like they share the eigenstates?
Yes,
that
is number 4, the complete set of the commutating operator, which I'm going to discuss next. topic, yes. So now, let's summarize here. So now, that is what means this is not commute, right? So if commute. If commute means here we have very easily get this case 0. So that means that's not dependent order. So that if commute, that definitely does not depend on order. Okay. The measurement. Does not depend on the order. So I just simply, so you know what means order, right? Order. Okay. With this conclusion, now we can come to the idea about this, or focus on the commutation, the commute. If they commute, that is more interesting, right? What the commute means, and as Tyler introduced the common eigenvalues or joint eigenvalues. Joint eigenstates. Okay. So now let's introduce the comparable observables. This number 4, okay, give it another set of observables. So what that means that if the two observables A and B, they are operators commute. Okay, in that case, then we call they are comparative or conflicting observables. That is a definition. And now, what that means? That means if they compatible, so they are measure B and A, measure A and B, you can simultaneously. That is what this is the means of what it means simultaneously. And the measurement does not depend on. Okay. So now let's go to the number 4. I think this is number 5, right? Number 4 is this measurement. So number 5 topic is now we are going to introduce complete side of commuting operator. Simulated as CSCO. So definition. Okay. If we have a side of permission operators, we have a set of permission operators let's say how many? A, B, C. Okay, all are permission operator is called CSCO if there are two conditions. They commute, mutually commute. Okay, first. Second, the side set of the common eigenstates. Complete and orthonormal eigenstate number 2. So normal and complete. So for that side, we call this complete side of commuting operators. Now why we introduce this, and you will see okay. Before we want to see this I think I need a little bit more. So before we want to discuss the feature of this, let's first give a theorem, which is very useful. Theorem 3.1. So this theorem says, if A and B are compatible observables, compatible observables, that means implied they commute, right? Okay. And they are operators. They are operators. A hat and B hat processes the side of C and CO. That is the theorem. So that means if they commute each other, or if these two variables are compatible variables, that means they commute, the corresponding operator commute each other, then they can form, or can form a side with their corresponding eigenvectors to form this side of this. They define this. Okay. So let's quickly prove that. Prove that we can have a common or joint eigenstates. Okay, so prove that, okay, let's say if the operator A has its eigenstates, then go to use A equal to A n. Okay, now I use psi instead of phi, right? So let's do that. Then let's look at this one. The sandwich of this commutator A and B between the states of eigenstates of operator A. Let's do this. And we know, so the left hand side, okay, let's do this. Let's just keep on it. A, that is AB, right? Minus M, A, B, A. Okay. Then you can see here A, since let's always discuss, okay, let's just exclamation, right? So now A, M, A, equal from A. We just only consider the Hermitian, right? So here it's be A star, but since Hermitian is real. We consider Hermitian since observables are physical quantities which correspond to operators be Hermitian. So now we just imply that. So this one, and then we have operator B, the sandwich between these two states. And the left hand side, the second term is this one. A applied the states of psi an, so that gives the eigenvalue of an. I don't need this one. And you see this is the same, so now I have am minus an multiply this inner product of the operator B between, or sandwich between these two states of eigenvalue, eigenstates of operator A. That is the consider before they commute, right? So that is now since A, B commute, so we have this sandwich between the commutator is 0. Right? So this term is 0, but this is just extended. Assume that we do not consider whether they commute or not. In general, it's like this. So we have 0 equal to am minus an times m a is b sandwich between these two eigenstates of operator A. Okay, there are two possible. So if this m not equal to n, you would argue this must be equal to 0, right? Since if not equal to n, these two values not equal to 0, then if ask this integral to be 0, right? Or it's not equal to 0. If m equal to n. So here I'm going to say, okay, yes. So now let's consider this case. That means if this is satisfied, that means the only choice, the only solution for this answer this is the B apply this eigenvector of A. So it gave us some constant or some constant multiply itself, right? Then that means this B applied to the eigenstate operator A is still the eigenstate of A, and then we have this inner product follow this. So this constant, okay, then we can define this constant is not, because this is a operator applied states equal to some constant multiplied states itself, so that is the eigenvalue of B, Bn, that number, right? So that means this eigenvalue states of A is also eigenstate of B when they commute each other. That is, so they have a joint eigenstates. At the same time, I will not, this is assumed this is non-degenerate. If degenerate is, we can extend in the same thing, similar way to make this. So in general, the complete eigenstates side of this computing operator, that is, which we use, if we use capital N, that's the products of our with this operator A with N1, and operator B is N2, operator C is N3. So that means if A, B, C, and mutually commute, and they can form the states. Each index is eigenstates of the corresponding operator A. Is B, is B, is C, is C. So that is the form is a joint eigenstates, or the complete side of this computing operator. Now they have to orthogonal and complete. So now there's one thing. If this is case, so we can see check whether we measure the first and the second, right? So now if we measure the first, let's just consider only these two operators, right? Yeah, whatever. So now, since this eigenstate of B and A, so that the first one, let's do this. First one is B and 2, right? So states B and 2, and then still states here. And then B and 2, I take and then A, multiply this will give A and 1. That is the first B and the second A. So now let's first A, second B. Do on the same states. So first is A and 1. And then second one is B to this one, right? So the A and 1, B and 2. Then you can see the probability. So here the probability, the B, let's see first, P is B and 2, A and 1 is 1 multiply 1, right? The states. And here, first is A and 1, B and 2 is also 1 multiply 1, so they equal. That is what happens if we have the joint eigenstates, and then if the initial, whatever, if the initial is not the eigenstates of this one, it's also fine. You can do the linear combination, but you will see the result same. So that means we can measure that does not depend on order. One more, just a few minutes, I want to mention something here. So examples of is a CSCO, right? So example, even if only one operator itself is form this complete and orthogonal, right? So this one operator itself can form because you know that is itself is complete and orthogonal. For example, if we have operator B, X position, right? So its eigenvalue is this definite form, so we know that is okay. Yeah. And some. Right, we know that. So that means the simple case is for single operator. Yes, it is. So that is the second one. So if consider this one, and they do not come in, right? Since they're good. So this the eigenstates of position operator and eigenstates of momentum operator, this cannot form the complete set of commutating operator because it did not come in. This is the second case. Silly case. So if A, B, C, okay, some of them okay, let's say just two. If A and B degenerate, they didn't discount degenerate, right? So in this case, the question how to form or build up this complete set of the commutation operator that we need to find the third one, to find C, for example, such that C is non-degenerate. Its eigenvalue or its eigenstate non-degenerate. It's non-degenerate. Then we can form the complete set of the computing operator for these three operators. Example, the hydrator, right? Since you're familiar with hydrator, so I just use hydrator. Hydrator we have Hamiltonian, L square, angular momentum, and LZ, right? Just ignore spin. So they mutually commute. So in principle, they can form this complete set of the commutating operator. However, let's just consider here this one. These two degenerate. Since we know, if you remember N, L, M, that is eigenstates of this hydrogen atom, right? So N corresponds to H, L is corresponds to L square, LZ. So for given N, we have a lot of states. The same energy, we have a different L and different M, right? So that's degenerate. Even for L, given N and L, we still have a different M value. So they do not, they both, if we only consider both H and L square, they cannot form the complete set of the commuting operator, since the subspace they still cannot determine uniquely. I mean the unique states to give this all this completeness and orthogonal. So in this case here, we need add that LZ, which is the non-degenerate if we do not consider spin. Then that is case. So now, then this one, okay, now let's see this one. This states is not CSCO. But then if we add the eigenstates of LZ, so we have the three quantum number, it is CSCO. That makes sense? I know I since already occupied states time. So I have to little bit speed up quickly, and I also cannot discuss the uncertainty principle, but that is that's okay. We already discussed in the chapter 2, almost there. So now, can you deliver or dispute this the midterm exam? I want to explain here because there's one question. Yes.
Oh, sorry.
You don't have a question?
No question.
Okay. So we have totally 5 problems.
I don't think that's enough.
Really? Totally we have 8 students, right? Oh, we have 9. Okay, then I got maybe one.
Did everybody get one?
Yeah.
I guess there was another one in there I didn't see.
Okay.
We're good.
We have 8 students, I think I cleaned up.
Yeah.
Okay. All right,
I
just
thought I
quickly
only
go
handed
through.
3 over there.
You don't have a class, right? So far? So we have 5 minutes? Okay. The first one is simple, just consider a single particle system. And it has a Hamiltonian either include kinetic energy and potential energy, and ask us if as this commute and the momentum and total energy be measured simultaneously means this will commute, right? So the question asks, if this one commute, the conditions you should here prove that the potential is constant. That makes sense? That is the first question. Second one gave you the Hamiltonian. This chapter 2, you have a lot of a kind of practice. So you see this is an operator, right? Because this is like the operator, this cat or bra, something like this. This kind of is operator. And then you see this is a two-dimension because we have only phi 1, phi 2 form the complete orthogonal basis. So you have to see that this be 2 by 2 matrix if the Hamiltonian. Then you just solve the eigenvalue problem and calculate trace and calculate the others. So I think that details you just do that. Number 3 is this. It's about the measurement. So we have operator A and B. In the matrix representation, we have a states, initial states. So ask us, first, A, B, are they compactable, means that the operator are commutable or not. Then prove that this orthonormal eigenstates of A form the complete basis. So that means you find operator A, this eigenvalue, and find eigenstates. So they make that summation of A hat and A bra equal to I. Go to that is, and then now we are going to measure. Measure A first and B second. Afterwards, find the total probability of obtaining the value for A is -1 over square root, and then B is value 3. That is probability. I think I have some example here, right? Then let's measure B first and A second, and find the same thing to find these two values, but what the probability, and compare the both. And then finally, let's calculate this uncertainty principle. Uncertainty, right? The delta A, delta B, and the commutator relation and the average. So that is number 3. It takes time because you need to solve the eigenvalue problem for A and the eigenvalue for B to find the eigenvectors. That's your homework 23, right? Number 4 is give you the Hamiltonian operator like this, and it say that find the states. So that is ask you to this. I hope you understand the question. So you have Hamiltonian, right? They say if give you Hamiltonian that operator there, and you find applied states and equal to this, so you're going to find. And in this case, this is in the position representation. So that is x. That is question asked. Or in so find this. That means solve this equation, right? Mathematically. And also and calculate another probability to find the particle in this range. So that is definition how you do that. And another operator A, and find that the eigen function of this operator A, and calculate the commutation relation. Number 5, give us the two operators A and B and try to see whether they are commute together, and if yes, and find each individual eigenvectors, eigenvalues, then see how to compute or form. This is what I said, how to form this. Form this means that you will see the Hamiltonian AH like the degeneracy. So you are going to find the complete side of the commutating operator that eigenvectors is not degenerate, so that because A is not degenerate, you will see that. So that is the topics asked to work on that, and find eigenvalue of H square, right? So you know, if you know H, you know how to get H square, right? And the commutator relation between H square and A form the complete set of commuting operator. All right, any question? If you do not understand the question, let me know. You either email me or stop my office. I will explain in details what the question asks, and you know how to do that. And for not like homework, right? You have to do yourself. Do not any communicate each other or talk together, right? So that is the regulation, and then on next Wednesday, just turn back. Then that's the due date. Okay, good. Any question? If not, I will say good luck. Hopefully, yeah, you can solve those. I think that is not hard. Yes, but it takes time. Really takes, yes, thank you. I'm going to turn yours on your mailbox. Over tomorrow you have another class, I can turn you, but for you, I will send back to your mailbox.
Okay.
And for you have mailbox, right?
Yes.
Okay, I will send back.
Do you make the homework?
Here, I think you can question for that. No, it's nothing but it should be the end, this is E, right? No, just the question on
Yeah,
this.
we have AB, so that is his C. Okay, sorry.
D and that is E, right?
CD, yeah, that is B. Thank you. Yeah, I will make I will also post on the. Increase N. Okay, yes, that's fine. Okay.
Okay.
So I don't need to. Yes. Thank you.
Like that, sorry.
Yeah.
So what you calculated in A, apply in C.
Yeah, C is for the result from A. Yes.
Okay.
Yes.
You need in? Yeah, sure. I can get it at a time.
No, I'm going in right now.
Yes, very nice. Same sir?
I got very low score compared to you.
Yes.